And we'll start from current slide. So, wow. We're getting started than I thought we was. All right. I finally did print off a couple of announcements. Didn't get to all of them. They may be expired by the time I finally get to the rest of them. It's just been such a flood of email recently. This is from a man named Jonathan Jefferson, and he must be a coach here at Lawson, but I don't know who he is. But he says it's a job offer. I'm guessing you're probably not interested, but you may know of someone who's interested. But I'm also recording this for other students in case they know of anyone or may be interested themselves. The company name is No Kid Hungry. Okay, the company description is No Kid Hungry is working to end child hunger in America today by ensuring that all children get the healthy food they need every day to thrive. The job title is Brand Ambassador. That doesn't say much to me. Here's the job description, 2 bullet points. Send out the items through the mail to the list of orphanage homes that would be provided to you in your city. Number 2, mailing out letters of invitation from us to other non-governmental organizations, foundations, and businesses in your city. So it sounds like it's partly sending out either supplies, materials, food, whatever, and then also participating in fundraising. Here's my take on those 2. Interested candidates should contact Henry via email. Now, that sounds really bizarre, but the email address is given is HS with about 7 digits following it, numerical digits, at gmail.com for more information. The weekly wages, $350, which seems a bit low on my standing, but I don't know. Maybe it's not that many hours work. I don't know. Thank you. Looking forward to hearing from you. Coach Jefferson, Lawson State Community College. So that's all I know about it. I assume it's legitimate. If I find out it's not, I'll try to pass that word to you as soon as I hear. Okay.
And you didn't get a title for himself.
He just said coach. That's all. So I know we have hired some new coaches recently. I know a few of the names, but I don't recognize his. His could easily have been, I may have heard it and just gone blank on it. Now this is an announcement I saw on the, posted on the wall on the Birmingham, Birmingham West Campus last Friday. And I hadn't heard anything about it, and I wondered about that. But this is sponsored. This is sent from the dean saying, LSCC faculty, staff, and students, please contribute to this important SGA, the Student Government Association drive. Thank you. And this is sponsored by the Lawson State Student Government Association and Ambassadors, 2 different organizations. It's a personal hygiene drive. All donations will be distributed to local homeless shelters. And it says November 13th through 22nd. Now, I don't know if that's when they're collecting them or that's when they're delivering them. I just don't know. I assume it's collecting since they sent it to us on the 19th, which is toward the end of this. Now, donation drop-off at Birmingham Campus Academic Success Center. That's that new building over on the Birmingham. It's on faces Wilson Road, but doesn't have an entrance from Wilson Road. You have to come in the school entrance and drive around to get to the parking lot. Now, here's the part that I found sort of irritating. Bessemer Campus, Student Activity Recreation Center. Well, I know where I think that is. That's across from the cafeteria. And I know there's a foosball table, maybe a pool table, a couple things in there, just a little rec room, maybe a TV. I'm sure it's TV. Okay? I brought in some stuff yesterday, and took it down there, and the door was locked. I said, well, it's early, maybe they'll open it until I had a 8:30 class, so I taught the class, went back, and it was still locked. So I went trying to find someone who worked in student services. I found Dr. Herndon, and I asked her about that. I told her about this, and she said, well, we don't have a student activities person anymore. That person quit or whatever, and so nobody's here, so no one unlocks the door. I thought, well, how can we donate items there? She said, well, I'll take them to the Birmingham campus if you want me to. And I was in a fog and said, oh, I'm going there tomorrow. I think it was Thursday and it was only Tuesday. Now I'm thinking I should give it to her to take over there because the deadline is Friday, and so I don't want to miss that. So anyway, as far as I know, there's no collection site on this campus. They may get one because I've emailed people about it, but it's running out of time. The recommended items are shampoos and conditioners, soaps and shower gels, combs and brushes, tampons and pads, lotions, deodorant, baby wipes, hand sanitizer, socks. And they didn't mention any dental stuff there, but they had a picture of toothpaste and toothbrush. I happen to have a box of toothpaste that hasn't been opened, so I brought that in. So I hope they'll take that. I think they will. So anyway, if you can care to contribute, please do so. I'll be taking some to the Birmingham campus on Friday, so and I may even get it to Dr. Herndon before that. So it's rather bizarre. Anyway, all right. Any questions on anything so far? Okay, yeah, right. All right. We are in Chapter 14, Multiple Integration, Section 14.2, Double Integrals and Volume. And we had done the double, we had talked about this. Example 1 is actually going to do 1, okay? But this isn't doing calculus, it's doing the summation stuff. So what a sort of a pain in the neck this is, but we'll do it, okay? It says approximate the volume of the solid lying between the paraboloid, which is 1 minus x squared minus 1 half x squared minus 1 half y squared, and the square region R given by 0 less than x is between 0 and 1 and y is between 0 and 1. And it says use a partition made up of squares whose sides have a length of 1/4. So between x equals 0 and 1, these would be partitions that would be 0, 1/4, 1/2, 3/4, and 1. 0, 1/4, 1/2, 3/4, and 1. Okay, got it. Okay. Sorry. Now, goodness, I think I'm sorry. It'll make me sound like I have a mouthful of rocks for a minute, but I think I better down a ginger chew. They're not really cough drops, but they help my throat make it feel better, about better than any cough drop I can recall. Maybe not all, but I love ginger. Okay. Now, it says use a partition made up of squares whose sides have a length of 1/4. Okay? They basically told us which one they were going to use, which is okay. You could have used others, but we'll use the one they said. So starting at 0, 0, I'm just going to sort of lay this out. Okay. This is 1/4. Each side is 1/4. So this would be 1, 0, 1/4, 1. Okay. Probably have it upside down, but I was thinking 3 space. Okay. Something like that. They happen to choose the center place, which is fine. So the first one, that's the point here, is 1/8, 1/8. This center point would be 3/8, 1/8. This one would be 5/8, 1/8. And this one would be 7/8, 1/8. And then you go on down, this would be 1/8, 3/8, and so on. 3/8, 3/8, 5/8, 3/8, and 7/8, 3/8. Okay, 5/8. No, 1/8, 5/8. I can't write. 3/8, 5/8. Goodness, this pen is messing up too. 3/8, 5/8. 5/8, 5/8. And 5/8, 7/8, 5/8. And this would be 1/8, 7/8, 3/8, 7/8, 5/8, 7/8, and 7/8, 7/8. Okay, those are the midpoints of each of those squares. All right, now the area of each square, if we're using the formula that we came up with before, that the volume of the prism would be the summation of, from, in this case it's n equal 1, or I equal 1 to 1/16. And then the function value at each of these, f of xi, yi, times the area, or the area of each one of these is 1/16, because they're 1/4 by 1/4. Okay? So you can pull that 1/16 out front, okay? And then have the summation of these, I equal 1 to 16. And then you evaluate this at each one of those points. And it's a real pain in the neck, okay? Just be very methodical about it and careful about it. And that would be, just for instance, the first one, 1/8, 1/8, would be 1 minus 1/8 by 1/8 is 1/16. And half of that was 1/32. So this would be 15/16 for that one, the first one. Okay. What I think I'm going to do, for some reason, erase my stuff. Oh, here it goes. This is really getting weird. So you do this for every one, okay? And I don't have room to write 16 function values down, okay? So I'm going to let them do the writing. But you see how it is. Sorry. I'm so sorry. Okay. Said then by forming specified partition of R, and they say it's convenient to choose the center, it's fine. This is exactly what I did. I wish I would have just gone with the slide. See, the X's are first and the Y's are second. And I've done it the same way they did, imagining 3 dimensions. Except even that's kind of backwards here, but anyway, it doesn't really matter where they fit in the thing, that these are the values you do. Okay. Now, and I have a feeling they don't show you any more than I have so far, because I was going to leave it to them. Because the area of each square is delta A is 1/16, 1/4 by 1/4, exactly what we said. Once Josh got here. You can approximate the sum of this. And again, they don't show you how. That first one would be, I think we said, what, 15/16? And you just keep adding them up. That's the greatest one. And they just say it's equal to 0.7672. Which, no, well, you got to multiply that by 1/16. I was going to pull that out and just do other sums and then multiply by 1/16. They don't show you any of that. But it's something that could easily be program a calculator, a computer to do, and maybe even program a calculator to do. It's not impossible, but it's just a real pain in the neck. To sit down and do each one of those. Now, a little bit easier thing to do would be for each, since the values just show up, just do 1/8 squared, 3/8 squared, 5/8 squared, and 7/8 squared. That's what you got everywhere, okay? And then, since every one of those is going to be multiplied by 1/2, take half of that. So 1/8, well, like I just did on the other one, but let's do 3/8 squared. That would be 9/64, and half of that cough drop didn't do much good, did it? 9/64, and half of that would be 9/128, okay? Rather bizarre number. In fact, I may have done the other one wrong. 1/64, 1/64. I think I doubled it. I didn't take half of it. That'd be 1, okay. My answer was wrong on the other one. Let's go back and correct that anyway. 1/8 times 1/8 is 1/64, and then half of that. Okay, let me erase this. I'm embarrassed now. Okay. Well, there it is. Okay, this was 1/64 times 1/2 is 1/128. Okay, and you subtract 2 of those, that's 2 1/28s. That's 1/64. Okay, we're back to that. and this would be 63/64. 1 minus 1/64. So that that first one, once you pull the 1/16 out, that first sum would be 63/64. Okay? The next one. And that's what I said. If you go in and do all of them, and do 1/8 squared, take half of that. 3/8 squared, take half of that. 5/8 squared, take half of that. 7/8 squared, take half of that. You got all the numbers you need there. Then do 1 minus that result and that result again. Okay, we already did that. 1 minus the 3/8 minus the whatever, the 1/2 x squared with that and 1/2 x squared with that. So it's just a matter of keeping up and being very careful with your distribution there. You sum all those up and then take 1/16 of the result, and they claim that you get, without showing you anything, approximately 0.672. Okay. Now, let's go back I think I'll clear this, all that effort I took to write it. Clear that, and let's just actually integrate that. Now the integral, remember, is the integral from 0 to 1, 0 to 1 of this function times dy dx, dx dy, whatever way you want to do it. It really doesn't matter here. That's what we would have. The double integral of this thing, 1 minus 1/8 x squared minus 1/2. I say 1. I don't know what I'm writing. Okay, x squared. dy dx, dx dy, it doesn't matter. Whichever you want to do first. You just have to put a d in each one of them. Okay, now before we just had, when we were doing areas, we just had a 1 in there. And that was pretty easy. Now we've got to do antiderivative. And these are both going 0 to 1, so it doesn't matter which order you're doing. Okay, so let's do 1. We'll do the dx first. We'll leave the y's for later. And do that integral. What would that be? X minus
1/6 x cubed.
Okay, x cubed over 6, good. Right. Yeah, you're doing the dx first. Well, 1/2 y squared x.
Oh, yes.
That's a constant, okay? I started off writing it weirdly, but, okay. And you evaluate that from 0 to 1. Now remember, these are x's 0 to 1, not y's. Okay. So, and then you're going to do your dy's later. So I wish I'd have written further over. So this gives us the integral from 0 to 1 of, let's evaluate that, 1 minus 1/6 minus 1/2 y squared dy. Okay. Now, I would combine those two to make it 15. Goodness gracious. 5/6. Well, my eraser's not picking up. 5/6 minus 1/2 y squared. Oh, I didn't do the 0. Sorry. 0, 0. Okay. Okay. Plug in the 1.
Oh, yeah.
And the 0s, you get nothing. Okay, those are x in every term. Okay. Now, do that integration.
Y.
Why not? Okay. Minus Oh, wait.
Yeah, we,
I'm sorry. I was doing the,
4-5Y.
yeah, 5-6Y. Okay, right. 5-6Y minus, what you say?
Y cubed over 6.
Y cubed over 6. If it'll ever write, there we go. And evaluate that from 0 to 1. I'll do the one part. No. 5-6 minus 1-6. That's 4-6, which is 2/3. And then the zeros give you nothing.
Oh, never mind. I didn't see the 5-6 of
Yeah.
in front of Y.
We
Yeah.
changed this to 5-6. 5-6 minus that. And we just get 2/3. 2/3 is 0.666667. And they got 0.672. Not too bad. Okay? Good to at least one decimal place and close to the second. Okay? Now, I probably wasn't supposed to do the actual thing, but we did. You can obtain a better approximation by using a finer partition with each side of each square equal to 1/10. Boy, you're going to have a lot of calculations on that one. They wouldn't show you anyway, but they said if you did it to 1/10, that would then be going a summation of I equal 1 to 100, because you'd have 100 then of F sub X sub I, Y sub I, delta A sub I. Okay? And they don't show you, they just tell you that would come out being approximately 0.668. Okay? So 0.672 to 0.668. Ultimately, we're going closer to 0.6667. Okay? You can do as many sixes as you want to. That's really, really close. I mean, very, very close. All right. Okay. They have a little technology note there. Since I don't have a device to do it on, I'm not going to. I'm sorry. Just having such trouble breathing. Oh, man. So, it says using the limit of a Riemann sum, which I jumped on and did, you come up with a double integral, and we've already done that. So here, I hope they will show. All right. I think we did this, but if in case I didn't. The approximation shown here graphically gives you 0.672. So that means the overestimates outweigh just slightly the underestimates. So the purples above this line are your overestimates, these lines, and your blues that are beneath that are your underestimates. So especially with this one here, the overestimates sort of outdo the under, but it's awfully close. It's awfully close. Yeah, okay. Okay. So, yeah. Here, I'm sorry, I wrote down the stuff. Here it is. You can use obtain a better approximation, use a finer partition, and the squares the sides of 1/10 would give you an approximation of 0.668, where they still know the exact is 0.6666666, 2/3. In example 1, note that by using finer partitions, you obtain a better approximation of volume. This observation suggests you could obtain the exact volume by taking a limit as that norm, is what they call this, is approaching zero. Okay? Define the norm as being the diagonal of any one of those things. So the maximum diagonal that we did. They're all the same the way we did it. And that would be limit as of the summation I equal 1 alpha x of I, y sub I, delta a sub I. These are all the same, but delta a sub I, the area is length times width, and if each of those is delta x and delta y, then that should delta x, delta y. And when you take that to be that the limit would be the precise meaning of that limit is that the limit is equal to L if for every epsilon greater than 0 there does exist a delta greater than 0 such that that absolute valued thing, the difference between the limit and your summation would be less than delta, less than epsilon, that you could find some delta that would make that be the case. For all partitions, del, or whatever you call that, in the plane region R, that satisfies the magnitude of that del seems like they're sort of mixing some terminology here. Less than delta, that's another delta. This one's an uppercase delta, and this one's a lowercase delta. They don't look at all alike. Seems like it's different. I guess it makes sense. And for all possible choices, x of I, y sub I, in the ith interval. We just arbitrarily chose the midpoint, but you could use any point. Okay. Now, trying to find where this sentence is in the text. Oh, here it is. Yeah. This is the right under the technology. In example 1, by using final partitions, you obtain a better approximation of the volume. The observation, yeah, this is stuff we've already said. I just didn't have the slides going in the right order. And there's your difference. Here's now the definition. Using the limit of a Riemann sum to define volume as a special case of using the limit to define a double integral. The general case, however, does not require that the function be positive or continuous. If f is defined on a closed bounded region of R in the xy plane, then the double integral of f over R would be, in this account right, some defined region in the xy plane. F of xy dA would be defined to be the limit we had just a minute ago. The limit is the norm is approaching 0. That's the maximum length of a diagonal of any of these divisions here. If that's getting smaller and smaller going to 0, then this would be the limit of this sum, I equal 1 to n. Now that n is getting bigger and bigger and bigger the smaller you make this. F of x sub I, y sub I, the a sub I. Provided that that limit does exist. If the limit does exist, then f is integrable over that region R right here. Now, having defined a double integral, you'll see that the definite integral is occasionally referred to as a single integral. I think what we talked about back before when we talked about a definite integral, Now we're going to refer to it as a single integral because it doesn't have a second. Because this is a definite integral too once you put the limits on it. So to get a little more precise terminology, sufficient conditions for the double integral of f on the region R to exist are that R can be written as a union of finite number of non-overlapping regions. Okay? Now, these regions need to be either vertically or horizontally simple. In other words, you can easily integrate them. And the F is continuous on the region R. Okay? Now, weird looking shape. But by choosing this to be your partition, now it's pretty
Pretty close to perfect simple.
yeah.
It might not be in the very, very end.
Yeah. The only place you would have some problems are over here, but still, I don't see why. They're just showing a partition. This is not one that produces vertically or horizontally simple, because vertically you're still going side to side. You're not going function to function. Okay? If you had done this one this way, now you could do vertical pieces on each one of them, and that would be fine. You go from max here to max here. They went not quite min to min, but pretty close to it. But you see, horizontals don't work well. Verticals, I guess, work okay. It's just over here and over here. You see what? The reason to put a partition in here is to use this line as a base. And that line would only be a base with horizontals, and they don't work well here. But if you did a horizontal line here, and then did this to this, and this one to this one, they all matches up pretty well. So what you want to do is get something where you have a defined function here and a defined function here. If you're doing this way, then you want a defined function here and a defined function here. You don't have it here because you have places where the roads. I think they just meant this as an example of what they're talking about here. An intersection of two non-overlapping, nothing overlaps between those two regions. This means that the intersection of two non-overlapping regions is a set that has an area of 0. And the area of the line segment common to R is 0. Of course, the line doesn't have an area. So I'm sure that has some meaning, but I can't quite figure out what it is now. This is just two non-overlapping regions. That's all that's illustrated here. Not that this would be your choice of how to do your integration from it. I think. I sure don't see it. Okay. So, a double integral can be used to find the volume of the solid region that lies between the xy plane and the surface given by z is equal to f of xy. Okay? If f is integrable over a plane region R, it means it integrates with x and with y, and this f of xy is greater than or equal to 0 for all xy's in R. Now, again, we're going to this requiring every value to be above, greater than 0, meaning you can integrate all of it in R. Then the volume of the solid generated, the solid region lies above R and below the graph of F is this. That's the graph F. Think of that as Z, and this is your dx dy. Okay, and you're integrating over the entire region. Represent that. Sorry. Double integrals share many of the properties of single integrals. Okay. Let f and g both be continuous over a closed boundary region in the area R. And a single integral that would be the domain of x. Okay. Then, and let c be a constant. Then the double integral of a constant times the function is the constant times the double integral of that function. In other words, you can pull the constants out just like we did. Okay? The double integral over a sum or a difference of two functions that are both continuous on this closed interval A, on this bounded region here. The integral of the sum or the difference is the sum or the difference of the integrals, the double integrals of those.
Just like normal.
Just like normal. Number 3, the double integral of the region of that is greater than or equal to 0 if f of xy is greater than or equal to 0. If this is positive everywhere, your double integral's got to be positive. Okay. Now, if this f of xy was negative down here below this, then you could come up with a negative value, which sort of grates. It doesn't seem like it makes any sense, but that's what we give it to you. Okay? Now, another one, if you have a double integral of the region R of f of xy, and this is always greater than or equal to the double integral of g of xy dA, that's going to be the case as long as f of xy is always greater than or equal to g of xy. And the last one, the double integral over the region R of f of xy is the level region over, this is your partitions. If you break these into non-overlapping partitions, all the points are covered, then you can do R, integrate first over R1, then over R2. R is a union of two non-overlapping regions, R1 and R2, and R is the union of that. No, nothing in common. The intersection of these two is 0, the union is 1. Okay. Now, I'm having trouble breathing. All right. Let's evaluate some double integrals. Consider a solid region bounded by the plane z is equal to 2 minus x minus 2y, and 3 coordinate planes shown here. When you say coordinate planes, that's the xy plane down here, the xz plane over here, and the yz plane over here. So those are bounds here, here, and there, and then plane, this plane is the one that cuts the corner there. Okay. Now, since it gave this to you, z is equal to function of x and y, that's your height at any place here, okay? For any of those values, x and y, that fits this. Now, just for a reference here, your base here, okay, just using this, okay, if you let x and y be 0, then this is going to be 0, 0, 2. If you let z and y be 0, then that would be x is equal to 2, right out here. If you let z and x be 0, then you have y is equal to 1. That gives you your 3 vertices, you might say. Of course, the other ones right there, 0, 0, 0, but we're only working with this one, the ones associated with that point. Okay. Now, if you picture this, the base is a triangle, a right triangle, because that right angle is in the corner okay? And you're going through the point 2, 0, 0, and 0, 1, 0. So the z's are really not in play too much here. And you can do that with point slope formula, double point formula, 2-point formula. Lots of ways you can do it, but you wind up with the base. Either way you want to do it. Let's see, I think it might be easy to do this way. At the base, z is equal to 0, right? So let's just take this. Rather than trying to work it out geometrically, let's just take the formula we got. When z is equal to 0, you have 2 minus x minus 2y is equal to 0. Solve that for y. That would be 2y is equal to 2 minus x. Divide both sides by 2, and you get y is equal to 1 minus x over 2. Or, if you don't want to do it that way, I could have left it just like it was, this way right here. That's how they left it. Sorry, I took it one more step. Y is equal to 2 minus x over 2. Okay, now, that's your base. Okay? Now, what you need to do now is decide how you're going to proceed with this. Okay? You could, with that base, do cross sections coming perpendicular to the y-axis, coming out like this. They chose to do cross sections perpendicular to the x-axis. Okay? Now, every cross section here is going to be a little triangle. Okay? I'm pretty sure these are all triangles that are similar to that big triangle over there as you go down. Now, the height of that triangle that they drew there is your set y is equal to 0 is one thing you could do. But you might argue, well, wait. But yeah, that's exactly what you do. This height here is where y is equal to 0. So that would be z is equal to 2 minus x. Okay? So that's pretty easy to determine. Now, what we don't, and I'm not quite seeing. Oh. Let me take that back a moment here. When I was saying the base was that, I was meaning that's a triangular base, but that doesn't quite give it completely to you. You're only getting the base of this triangle. And they say that's equal to that. For any value x, that gives you your y. Okay. All right. I guess I'll have that. There were no, well, so first we're going to do an integral to get the area of this triangle, all of those triangles, okay, in terms of x's. This is in terms of x, that's in terms of x. Everything will be in terms of x. Then your last integration will be to integrate that result from 0 to 2. Now, you could have done the same thing over here, and it would have been all right too. They show it this way, so let's go with it. So we'll first do the area of this, and that's 1/2 the base times the height. And unless they're going to show that somewhere else, let me see. Yeah, they do show 1/2 the base times the height. I said they sure aren't showing it on here. So each vertical cross section taken parallel to the YZ plane is a triangular region whose base has a length of y is equal to 2 minus x over 2, and whose height is simply 2 minus x. Okay? Now that implies for a fixed value of x, the area of the triangular cross section is 1/2 the base times the height. Here's the base, there's the height, and that gives you 2 minus x squared over 4. Now, that happened to work out just because, if you go back to your picture here, the value that's parallel to the y-axis is always half that of the x-axis, okay, as you're coming here. Now, you probably don't think of doing that, but that's what you're doing. You're starting out with, man, this my head hurts. Here where this is 1 to 2, 1 to 2 this way, 1 this way, 2 that way. So that same ratio, because this is a similar triangle here, they're always going to be 1 to 2. So since the y value is, we solved here, is x minus 2 minus x over 2, the height is going to be twice that. So that's why these are so similar, okay, because that's a triangle whose legs are a ratio of 1 to 2, okay? So probably beating that to death, but that's why that looks so similar. And it's also why you have just a square up there rather than some other polynomial. Okay, so that's your area of the base, okay? It says here, by the formula for a volume of a solid with known cross sections, the volume of the solid is the integral. Now these are the areas of all those cross sections. Big over here, getting smaller as you come here. From A to B, A being the 0 to B equal 2, 0 to 2, of this area times your dx. Because we already did, in a sense, your dy. So, well, leave that for now. Now, the way they do the integration is to just say, this quantity is the thing squared. So we'll have this quantity cubed over 3, and 3 times 4 is 12. But it's going to be the minus because of that minus sign in there. So it's minus 2 minus x cubed over 12. Evaluate that from 0 to 2. And when you put a 2 in here, that gives you 0 here. And put a minus your 0, and that would make it a plus here. And that would be 2 cubed over 12, which is 8 over 12, which is 2/3. I think. Hope my cells are cooperating well today. That procedure works no matter how a sub x is obtained. That area that you're dealing with, that volume, of a slice of the volume. In particular, you can find A of x by integration, as shown in this figure. Okay, what do we mean by that?
What's that little triangle?
Yeah, it's this thing, and what I'm trying to see is here you got dy's going on. Oh. This is that. This is this little blue triangle here. That's what that is. Okay? Base 2 minus x over 2 by 2 minus x. I sure hope that's what it is anyway. Yeah. Y is equal to from 0 to 2 minus x over 2. They don't show you what the peak is. But we do know when y is equal to 0, which would be that would be that. So yeah, that's that triangle. So what they're doing here is showing you how they got the area, this area, from that triangle. Well, the height is your z. That's your z, whatever your values are. And the integral of this thing is then the dy is your base, the height is the z. So you would be doing an integral from 0 to 2 of this thing dy. Okay? And let's do that. They didn't do it.
So on this picture, you've got 4 triangles basically. And if you can find the area of all of them, could you find the volume that way?
Okay, say that one more time.
So there's 4 triangles on this.
Right.
This plane.
Right.
If you could find the area since you know all the points, could you find the volume that way?
Okay.
By knowing the area?
Not. Okay. If what I'm hearing you say, if you knew the area of the base, if this were going straight up, yeah, you could do it that way. But this is slanting in like this. So everything's changing with everything else. The links along here, the links up here, all the links are changing. But they're changing regularly according to that triangle. That's what they're evaluating first. So they've gone about this in sort of it feels like to me a backward way, but let's go back and see what they're doing here. They're not showing it, I don't think. So let's find this area. This is the area, just the area of this triangle. The area from y is equal to 0 to y is equal to 2. Yeah, okay, of this thing here. Well, no, y is equal to 2 minus x over 2. Okay, that's as far out as you go on y. So you see it's not going all the way to 2 on every triangle. On this one it's going here, okay? Now, your height here is the z, which is 2 minus x minus 2y, and then you're going to do a dy, okay? That should give you the area of that triangle. Now, they acted like you knew that already here by using this. Let's see if you get the same thing doing it this way. All right. Now, you're keeping x constant, so this is going to be, and you can have constants up here too, okay? So this would be 2 minus x. It's supposed to be an x, okay? I'm so sorry, my eyes are, aren't working well. It has to do with the pain behind them, I think. I have so much congestion that I think I've got what they call a sinus headache. Okay, and it's not nice. Okay. I don't even know what I was starting to write up there. But anyway, let's integrate this with respect to y. So this would be what? Integrating 2 with respect to y. 2y minus xy. I think that's what I was going to do. 2 minus x times y. I think that's what I was starting to write now that I think about it. And then you would have a minus y squared. Evaluate that from 0. Y is equal to 0 to 2 minus x over 2. Okay, that's what you're plugging in for y. So this will be a 2 times 2 minus x over 2. That comes out nicely. Okay. Minus x times 2 minus x over 2. Okay. And then you have minus a 2 minus x squared over 4, right? That's the y. This is y equal this, or this y that you're plugging in here. Oh, there's a squirrel in there. I couldn't find it on the board. So 2 times y minus x times y minus sorry, that's squared. Okay. Now, I kind of regret doing this. I wish I'd have done it this way. But you can go back and redo it. But if we, rather than this, had done this one, and this is what these two become. So that would be 2 minus x times 2 minus x over 2, okay, minus 2 minus over 4, 2 minus x squared, okay. However you do it, this comes out with 2 minus x over 2. This, or 2 minus x squared over 2. This is minus 2 minus x squared over 4. So that gives you a 2 minus x squared over 4. Because if you made this one 2 over 4, then 2, yeah, that would come out exactly the same. And that's what we got doing it this way. 2 minus x squared over 4. So you could do it using the integral. Now here's what they're getting at. I know this is so much of a backward feeling way of doing this. What you actually did then, if you realize this thing, no, I'm sorry, yeah, this thing, here is the area part of this, right here. What we were just doing here, this thing right here. So what you had here is the integral from a to b of this thing, which is the integral from 0 to 2 minus x over 2 of your f of x, f of xy, which was your 2 minus x minus 2y, was it? I think it is. I can't read my writing now. And then you did your dy first, because this first integral was inside the dx next. Okay? Then what this is another way of doing the double integral you did here. Here we did it, doing the area first, and then go ahead and do finding this area. This way shows you if you had done this integral here, that would have given you the same area. Okay? 2 minus x here, 2 minus x squared over 4. And that's exactly what we got up there and there. You know, both ways we did it. We got there. So rather than having to find out on your own, just let the calculus do the walking for you, okay? The only tough thing in here, if you let this happen, is figuring out what this expression is, okay? And that's going to be the y. Yeah, that's going to be, happens to be that y here. Is that also, yeah, you're going from 0 to, yeah. For every one of those things. So if you go back, let's see what the next slide is. Okay, I think it's saying the same thing I was. Okay. If you could blow this up, this one down here, here's your y here, here's your z here. We're not really using that z at all, but we're doing the area here by taking dy's first and going from your z, not this z, but this z, because that's the equation you're playing. The key here, you're going from 0 to this value here, which is 2 minus x over 2. So that's the first integral. The innermost integral is integrating this shape, and then the second integral is your dx's running from 0 to 2 of exactly what those rectangles was. Now, I know I've sort of botched it up trying to explain how they did it their way, but let's proceed from here, okay? It's somewhat bizarre, but it's fine. That is, if you consider x to be a constant, that's on that one triangle there that you have. Let's go back to this one. That one. This triangle, x is a constant, okay? So you're integrating dy's up to this value from 0 to that value. That's the height. And from here, and this, that's what I said, finding out what this limit is here. In terms of x, that was your y is equal to 2 minus x over 2. And where we got that was setting z equal to 0 and getting this in terms of y as a function of x. And that's exactly what we got this value here. And then that first integral is going to give you the area of that blue triangle. Second integral is going to sum all those blue triangles from 0 to 2, and that gives you your value. So that's, seems like he could have said that. Maybe he did and I just missed it, but that's what he's trying to get at here. Okay? So you consider x to be a constant, integrate the z minus 2, x minus 2y, that's the height, from 0 to whatever the function is of y when z is 0. This is the upper, this is the lower, okay? And that gives you the area function. Seems like he's just done this already. And then when you integrate the area function, you get it as well. This one gives you that. This one then does from x equals 0 to 2. It sums all of those together. All right. To understand this procedure better, if it helps to imagine integration as two sweeping motions, for the inner integration, the vertical line sweeps the area of a cross-section, and for the outer integration, the triangular cross-section sweeps out the volume. So what he's saying is, wherever you start, doesn't have to be this end piece or wherever it is, any of these, that line, which is your dy, and your z is your height. So z dy written in terms of things you got. Going from, the problem with doing it here, you're tempted to do 0 to 2. It's not 0 to 2. It's 0 to this length here. And that length there you get from setting your z equal to 0 and figuring out y is a function of x. That gives you where it's going as a function of x. Okay? Then you integrate, that gives you a triangle there, and then you let these triangles sweep. That's what I was trying to say, from 0 to 2, and whatever your x limit is there, and that gives you your whole y. Okay. He sure picked a weird way to present that, but I probably botched it up because I couldn't understand what he was trying to get at in the first place. But here is an important theorem, okay? An Italian mathematician, Guido Fubini, and boy, he was fairly recent too, I mean, so to speak. He died just 6 years before my older brother was born, so I mean, he was about my grandmother's age. No, born about the same time my grandmother was. She lived a lot longer than he did. The theorem states that if R is vertically and horizontally simple region, and F is continuous on R, then the double integral of F on R is equal to the iterated integral. Okay? So, let F be a continuous on the plane region R. Continuous, yeah. Nice, smooth, everything. If R is defined from A to B on X, okay, this region is defined A to B on X, and on your Y, it's going from some G of X, G2 of X to G1 of X, G1 of X to G2 of X. This is the lesser, that's the greater, where the G1 and G2 are continuous on A to B everywhere. See, they depend on X, and X is from A to B. Okay. So what we do then is the double integral of this function F, which is the defining function, the Z you might say, dA, is the inner integral is from G1 to G2. In our case, the G1 was 0 and the G2 was at 2 minus x over 2. Okay? Only functions of x, or constants, that's fine too, but no functions of y here. Okay? Integrate that with respect to y, this thing, only keeping x as a constant, integrating with respect to y, and then plugging in these values for your y's, because that's your y values. Then you get a function only of x in here that you're integrating from a to b dx. Now, if on the other hand, R is defined from C to D on Y, okay, and from H of Y, H1 of Y to H2 of Y on X, okay, where H1 and H2 are continuous on that interval from C to D, then your double integral of this function R, of this function F over that region R by dA is the inner function is now your limits of whatever shape it is that f of x takes when y is equal to a constant. F of x, y takes when y is equal to a constant from the lower to the upper with respect to x, but these are functions of y, then this gives you, when you integrate this, the x's go out, leaves you only functions of y. Integrate that function of y between C and D. Okay. So basically, Fubini's theorem said you can do it either way, whichever makes the most sense to you or is the easiest integration to do. So let's try one. Let's evaluate. Oh, we've seen that before, haven't we? I think we've already done it too, didn't we? Remember? Okay. But we didn't do it by, well, we did. We didn't put the limits on. Well, yeah, we did. Because this was just a region 0 to 1. Okay. So you don't have to do, let me make sure of this, because the region R is a square, it's both vertically and horizontally simple, you can use either order of integration. So there's no function of x or a function of y as a limit here. So we've already done this, and we simply, I'm not sure that's very helpful at all, but it doesn't matter which one you did first. They chose to do, this is your base, this is only your base. And you're first doing with respect to x. I swear that it looks like they've done this backwards. They said choose dy dx here, which is fine, this is good. But then you would be doing, well, here's what they're doing here. I see what, now, all this mess on the board. What you first do is the area of the strip, and that's this thing from 0 to 1 of f of x dy. And that's your dy is here. And you find the area of the strip, and then this one is summing all those areas from 0 to 1 of x. So that's what it was. I wish, I don't know if this is, you first do this, where this is your dy, and you go from 0 to 1 there. That's what the inner integral is doing for you, okay? And then you sum 0 to x, 0 to 1 for the x to get you the sum of all those rectangles. A little bizarre because it's such a thing. Because the region is a square. That's fine. All right. So this is what they say to do. Again, either order would be fine. And this is exactly what we did. I don't remember which order we did the dy dx. Do you? We probably did. It's going to work out the same. So let's do it this way. The integral from 0 to 1, the outer one we're going to leave alone, and the dx we're going to leave alone. So let's just integrate that inner one with respect to y. That's why in problems like this, sometimes I like to put y equal here. So I remind myself, we're integrating with respect to y, not x. So what would this give us? Y minus 1/2 x squared y. Perfect. Y cubed over 6. Is that what you said? Okay. Now we're going to evaluate that from 0 to 1. Okay. This is y equals 0 to 1. Okay. So let's keep this down one more time. 0 to 1 dx. That's going to stay. So you plug in a 1, you get 1. 1/2 x squared, 1 over 6, okay? And that winds up being the integral from 0 to 1 dx of 5/6 minus x squared over 2. And, come on, that 2 is going to disappear in a minute, isn't it? Well, maybe it won't. Yep, I knew it would. Okay. All right. And we don't need the parentheses. Integrate that. 5/6x minus x cubed over 6. Plug in 0 to 1. I'll do the 0 part. Okay. You get 5/6 minus 1/6 equal 4/6 equal 2/3. Exactly what we got before. We did it, like you said, dx first and then dy. It doesn't matter. And Fubini's theorem said it shouldn't. Okay. Now, that was example 2. Let's watch how they did it, just to see if they do anything either bizarre or more enlightening.
I don't know why they do that.
Yeah, well, it's what I said you could do. since this has no y dependence, you put this is a constant. Both these terms added together is a constant. Someone out there?
I just heard a bunch of keys rattling.
What's that?
I just heard a bunch of keys.
Oh, I see. Maybe they like this. Okay. We're not going to leave. Okay. These have no y dependence, so they treated this as a constant. Constant times y. That's what they.
Yeah, I mean, it makes sense.
To me, that's excessive and doesn't make a lot of sense. But it's fine.
Think too much to do that.
Yeah. Okay. And then let's evaluate that next, like we did. And that would be 5, 6 minus 1 half x squared. When you plug in a 1, they manipulated some terms there, but it's okay. And then integrate that, 5, 6x minus x cubed over 6 from 0 to 1 is 2/3. Just like we did. One little weird thing they did. But other than that. Now, they're moving on to average value. We've still got somehow to, oh no, okay. Sorry, I misread. Here's example 3. Finding volume by a double integral, and this is on page 983. Find the volume of a solid region bounded by the paraboloid z is equal to 4 minus x squared minus 2y squared. Okay? This is pretty close to the one we were doing earlier. No, not close. It's sort of a mix between the two, but no, it's neither one. Okay? And the xy plane, that means z is equal to 0. Okay? When you see xy plane, just think z is equal to 0. Okay? Yeah, and that's what they do. Okay? As shown in figure 1417, which they don't show, and I hope you don't want me to draw it. You both can see it? Please, thank you so much. Okay. It looks like a thimble you would, or a rub or something you'd put over your little finger or something, whatever. Okay. Now, find the volume of the region bounded by that paraboloid and the xy plane. Now, looking at that, that is symmetric. I'm going to do it slightly differently. What you got in quadrant 1 of the xy plane is exactly the same as you got in quadrant 2, 3, and 4. Now, I don't know if you believe me on that. That's an ellipse in the xy plane with a major axis on the x-axis and minor on the y, but because all those are the same, so in my mind the easy thing to do is just take the first octant, and let's do that and multiply by 4. Are you okay with that? It'll be doing the problem a little bit differently, but it'll still work, I think. Okay, so let's just do and they happen to choose, so I'm going to do what I just said and do y here and x here, and x comes out to 2 on the, that's not very evenly split, and I'll do 2 up here too, but I'm trying to find my problem here. See, I would divide everything I'm sorry if I know this is better written this way, but I'm going to write it like this too. X squared minus 2y squared plus z is equal to 4. That's fine, isn't it? Okay, let's divide everything by 4. X squared over, that would be 2 squared, minus 2 y squared over 4. I'm going to leave that as 4 this time, and this over 4. Okay? Now, this now is a 2, right? Or the square root of 2 squared. Okay, I'm going to get the 4 completely out of that picture. Okay? The square root of 2 squared. So that means on the x-axis, this is what I'm trying to show you, it goes to minus 2 to plus 2. We're only going to do this like that. Up here you go to the square root of 2, which is 1.414, because that's your thing. So basically we're doing this portion of the ellipse. Okay. Now, they happen to choose let me make sure I'm looking at it right. DX's. So I'm going to try to choose one similar to what they chose. Okay, there's a DX. Okay. Now, what they're going to do is find the length of this and
hold on. So we got x squared over 2 squared.
yeah,
And then we've got,
y squared over square root of 2 squared.
but it's a plus, right?
Yeah. You're right. I'm sorry.
And 2 squared,
When I moved to there.
or the square root of 2 squared is going to cancel out because we divided by 4.
Yeah, it was a 4 down here. We divided by 4, and then the 2 went into 4 2 times. So I wiped out the 2. Yeah. I should have wiped out the 2 up here when I wiped out the 4 down there. I'll just keep him from writing it again. Okay. So what this means is, another way to write this, and maybe it'll make more sense than x over 2 squared plus y over root 2 squared plus z over 4 is equal to 1. Now, what that defines is this is an ellipse in the down here. That's your base, and your z is coming up here, actually going back into the board, coming out this way. Well, yeah, coming out this way. So we're first going to do the area of this thing, okay? Now, where z is equal to 0, which is down here on the xy plane, z is equal to 0, you have, which way you want to do it? X squared minus 2 plus, I keep putting a minus, plus 2y squared is equal to 4. Yeah. When z is equal to 0, move these 2 to the other side, and that's equal to 4. Okay? Now, we want to get, because the last thing we're going to do is our dx's. We're doing your dy's now. And this is going from where? Let's solve this for y. Okay? So we got 2y squared is equal to 4 minus x squared. Divide both sides by 2, and you have y squared is equal to 4 minus x squared over 2, and y is equal to, normally we'd say plus or minus, but we're only dealing with the first octant, so let's keep it plus. 4 minus x squared over 2. Okay, so that's this value here. That's where your y is going to. So we're going from 0 to 4 minus x squared over 2. Okay. And then we're going to sum those from 0 to 4. Okay. So what does this mean? Say again. Yeah, I'm sorry. I didn't write my square. I said it and didn't write it. Okay. But, so that's just the setup. Here's what we're going to do then. Find the volume, is that what it said, of the solid region? So that volume of the solid region is going to be 4 times the double integral. We're going to do our dy's. Yeah, dy's first. Y equal to 0 to y is equal to the square root of 4 minus x squared over 2. That looks like it's going to be a nasty bear, but let's see. And then the last is going to be from 0 to 4. I would have been much happier doing it the other way, but I'm trying to do it the way the book did. Okay? Now, and that would be of this integrand, the z, because that's going to be the height of these things. Okay? So that's going to be 4 minus x squared minus 2y squared. That's what z is. And then this is your dy first, and then the dx last. Yeah. Okay. Let's see if we can do that. 4 times the integral from 0 to 4. Let's see if we can integrate that with respect to y. What would that be? 4y x squared y cubed. Right? Okay? Evaluated from 0 to the square root of 4 minus x squared over 2. All that's under the radical. And then we'll have our dx here. Okay. Now, we're going to come up here and try to write that integral down. 4 times the integral from 0 to 4. Okay. Here we have another 4. Lots of 4s here, aren't there? That is a 4, isn't it? Yeah. Okay. 4 times the square root of 4 minus x squared over 2. I hope that's a 2. Minus x squared times the square root of 4 minus x squared over 2. Minus 2/3 times I don't know how to write this. I'm going to write it as 4 minus x squared over 2 to the 3/2 power. Isn't that right? Go ahead. Okay. And then when you do the zeros, that doesn't produce anything else. All right. Now this is a mess. Okay. It looks like anyway. And this is going to be the dx. Now wait a minute. What a trick they pull here. Okay. All right. Yuck. All right. I'm going to rewrite it the way they do, I think. I'm going to try anyway. 4 times the integral from 0 to 4. Okay. Let's factor out this, okay. We're going to have a 4 minus x squared times the square root. They like the square roots. I don't. I'm going to get rid of the square root and call it to the 1/2, okay. 4 minus x squared. Yes, over 2 to the 1/2, okay, minus 2/3, 4 minus x squared over 2 to the 3/2, okay, dx. Now I got to erase some stuff, and I think I'll come down and do some here. But here's what the note here. If you wrote it the way they did, which we objected to before, but it actually worked out pretty nice in this case, because you see you had both of these. This is from doing these separately, like we did, you know, a y there. They kept them together. 4 minus x squared, this, right here, factor out that, okay? Minus 2/3 times this thing here, 2 to 3/2. Now, here's the magic. I wish my board was not so dirty, okay? I'm going to erase a lot of stuff. I guess I shouldn't erase my original problem. Are we already past time? Way past time, aren't we? Okay. Let's come back to this one next time. We won't have to set up everything, but we can pick it up and do the integral from, I'm going to try to find a good place to do it. I'm going to start right about there. Okay, sorry. I thought at first this might be relatively simple, silly me. Okay, homework exercises here, 3 or 5, they're both at Calc Chat, 3's at Calc View. Any of the odds 7 through 11, they're all at Calc Chat. Any of the odds 13 to 19, they're all at Calc Chat, 13's at Calc View. And then you can start working on some of 21 to 25, they're all at Calc Chat, 23's at Calc View. And we'll stop there and pick up the rest of those later. Sorry. When I saw what they did in solving the integral, I went, oh my word.
I want to Google that because I've never seen what Wallace's formula.
Well,
I don't know if I have. That's what they use.
Yeah. Well, we don't have to actually use it, but we will.
Looks like it made it easier, maybe.
Oh, absolutely. But it's not hard to calculate either. Yeah, but if you look it up, I bet in the index, you'll see exactly where they referred to it. I remember it, but I don't remember which section it was.
It kind of looks like they said trig substitution.
What's that?
They said 8.3.
8 point. Oh, they said that.
Oh, yeah, it's right below.
Yeah. Section 8.3. And it'll be on page 534, if that helps too. It's just actually Wallace came up with this formula that we use in calculus. He was one of the teachers of Newton. So they calculus hadn't been invented yet. He came up with it empirically without the use of calculus. He had to have been a pretty sharp dude. Okay. All right. Anyway.
How people